right. Optics. Phew. So dusty. Maybe if I just use this dry rag to wipe them off, that's a little bit better. I don't want to scratch these really slick lenses or mirrors. So this is a mirror, and it's a concave mirror. Concave and convex. Think about like something is caving in on you. That's concave. Like when you go into the cave, the cave is caving in on you. And then something that's convex is moving away from you. It's like, you vex me, go away. So anyway, this one's convex. If it curves in on you, it's concave. If it curves away from you, it's convex. And these are my really slick mirrors. If it was a little bit sunnier, we can go outside and set stuff on fire with them. But well, there'll be time for that because spring is on its way. Spring is, it's almost March, so spring is on its way. Somewhere around here is the remote. Okay, so optics is the travel of light through various media. And we know that when wave energy goes from one media to another media, some of it gets refracted. When we were talking about sounds, we were talking about how waves could be basically transmitted through the material or reflected off the material. And the differences in densities determine how fast the waves travel through that material. Well, optics basically works the same way, but things are a little different with optics in that with sound, the more dense the material is, the faster it goes. With light, the more dense the material is, the slower it goes. Wow, my little remote is just tore it down. Put this up, take that too. I hope this sub didn't take that remote too. I'm sure it's around here somewhere. But why would a sub take remote? I mean, I can understand why he would take 3 colored pens, but yeah. He must be just one of those guys that like uses a pen and then puts it in his pocket. You might notice when I grade your work, I use different colors depending on what day I grade it, so I know which things come in late. Well, he used my colored gel pens, my purple and orange and pink colored gel pens, to take the roll, so I know they were here, but then they're gone. So they're nowhere to be found now. Okay, well, I will just...
Wait, are you looking for your little...
Yeah. See it?
I think it's in the second one, because we were using it for the laser. I think it might be in there. If it's not, there it is.
Yay! Are my pens in there? No. Too much to hope for. Okay. No, anyway. All right. So when wave energy propagates through a medium, it has to go from atom to atom to atom. So the first atom swallows it up, transfers it through, and then spits it to the next atom. Next atom swallows it up, transfers it through the atom, spits it to the next atom. So it's kind of a slow process when there's a lot of molecules that have to absorb and re-emit the energy. If a photon just travels through a vacuum, it travels at our favorite number. How fast does light travel through a vacuum?
3 times 10 to the 8.
Yeah, it travels at 3 times 10 to the 8th meters per second, which is pretty fast. It's the fastest anything can travel at any time. Now, despite what you see in cartoons, we don't have looking beams that go out. Okay, there's no reason that Supergirl and Superman should shoot energy out of their eyes, but they do. Understand that we see things because light illuminates the environment, and that environment then either re-emits the light or reflects the light, and the light ends up into our eyes. So in this first diagram, is the cat seeing the fish, or is the fish seeing the cat?
Fish sees the cat.
Fish sees the cat.
No, cat.
In this first diagram, the cat sees the fish.
Yeah.
The environment is illuminating the fish, the light is reflecting off the fish, and the cat is seeing the fish. In the second diagram, light's traveling this way. In the second diagram, the fish is seeing the cat. The environment is illuminating the cat, the light's bouncing off the cat and ending up in the fish's eyes. Okay? And Actually, the cat doesn't see the exact fish. It sees it in a different location because the cat's brain plays tricks on the cat. And here, the fish doesn't see the cat. The fish sees it up here because the fish's brain is playing tricks on the cat. And this is called refraction, and we're going to get to it in a little bit. Okay. We're going to talk about the refraction in a little bit. You've all seen refraction. When you put a pencil in water, the pencil gets kind of fat, or the straw gets really fat because the light travels through the soda or the water at a different speed than it travels through the air. These are lenses, and we have boxes of lenses we'll play with later. So this is called a convex lens. This is a concave lens. And as light travels into the lens, it bends a little bit. And it bends more where there's more lens material. So the light will always bend towards the fat part of the lens. Here, light bends towards the fat part of the lens. Here, light bends towards the fat part of the lens. These two lenses have a name. This is called a converging lens. This is called a diverging lens. Can you see why it's called a converging lens? As the rays converge. Can you see why it's called a diverging lens? Rays diverge. Okay. And I have a bunch of lenses up here. Most of the lenses that I can buy are convex converging lenses. Like this is a cheapo magnifying glass from Walmart. This is a less cheap magnifying glass. And then, wait, my big one is still here. Oh well, it's not. I have a really nice glass one that's this big, but it's missing because somebody took it outside last year to fry ants and it never came back. So this is kind of a nice one. This is glass, converging. Here's my favorite. These two lenses are from an old overhead projector. It's two pretty fat converging lenses that I've put together. Kind of blurry, but you can clean it up later. And then I have this other kind of lens. It's the other kind of lens from an old overhead projector. This is called a Fresnel lens. And Fresnel lenses are made by tiny etchings in a piece of plastic or glass. Pretty cool. So anyway, I got a bunch of lenses. Moving on. There we go. Okay. So when light beams reflect off a plane, they come in with momentum and they leave with momentum. And we say that the ray going in and striking the surface is called the incident ray. This is the incident ray. And the ray going off the material is called the reflected ray. And we measure those rays to what's called the normal. Now, this is the same normal where we got the word normal force. Okay? You know that a normal force acts how to a plane? Perpendicular, exactly. You know that a normal force acts perpendicular to the plane. So if you're standing on the floor, you have a weight pushing down and a normal force pushing up. Normal force always acts perpendicular to the plane. Even when you have a inclined plane, normal force will always act perpendicular to the plane. Well, a normal, in this case, is a plane that is perpendicular to the plane of impact. Let me show you what I mean. I got myself a laser. Oh, here's my laser. And on the laser, on the whiteboard, I have taped a tiny mirror right there. I've tried to tape it as well as I could to flush against this boundary here, this border. So if I shine the laser and hit the mirror, point to where you think it's going to go. Where do you think the dot's going to show up? Oop, there it is. It's on tin. Or iridium. Okay. So I can also change the angle and come way over here, and if I hit it now, where it is. Yeah. So this is called the law of reflection. And the law of reflection states that the angle of incidence and the angle of refraction will be the same as long as they are in the same medium. The angle of refraction, or the angle of reflection and the angle of incidence will be the same as long as they're in the same medium. In this case, air on that side, air on this side. Here's the thing though. You always measure your angles to the normal. And if this is the plane, then where's the normal? Yeah, cutting right through the middle of the room. Thanks. Right through Angelina, Sarah, and Landon. There's a plane that runs right through the middle of the room. If this is the plane of impact, then the normal is right here. Okay? So we would measure from the normal to the angle to where the incident ray is. This is the angle of incidence. And then from the normal to where the reflected ray is, this is the angle of reflection. The angles are always measured to the normal. Inside angle, not the outside one. From normal to Byers, and from normal to laser dot. Make sense? Okay, so assuming the medias are the same, and they are the same airs on this side as is on this side, then the law of reflection says the angle of incidence is going to be equal to the angle of reflection. How are we doing so far? Good? Should we move on? Okay. Sometimes you see these angles written with just a little I and a little r, but more often than not, you're going to find a theta I and a theta r. We like to use theta for angles. Same theta you encounter in geometry and pretty much all your math classes. We like to use theta I and theta r. Okay, so mirrors. 3 types of mirrors. There's the mirrors that you have in 7-Eleven. There's the mirrors that you have when you put on your makeup. And then there's the mirror that you have in your bathroom so you can see pretty much the rest of you. Okay, you've all encountered all these mirrors. A flat mirror is just that. It's a flat sheet of reflective material. Like that which you have in your bathroom. Whole flat mirror. Flat mirror. I can go, let's put it somewhere else. Let's put the presentation on your face. Hey, look, it's a flat mirror. So flat mirrors are fun. They're good if you want to see what you look like. It's like, oh, so that's what I look like. Sorry. What does a flat mirror do to an image? Nothing, right? But here's what's weird about a flat mirror. Take it to the Aboriginal people and freak them out. Okay, Taylor, where are you in the mirror?
I can't see myself.
Oh, okay. Where are you in the mirror?
Oh, I'm normal.
You're over here. So, believe it or not, the room doesn't actually extend into the mirror, but it does look kind of like it does. So when you actually have, or you're like, hey, look at all those kids inside the wall over there. You're like, hey, look at all those people like on the other side of the wall. So it appears to us that things are going on behind the mirror. Are things actually going on behind the mirror?
No.
No, but our brains have to put the light somewhere, so our brains say, let's just say it's right over there. So this gives us a special kind of image. So light strikes a mirror. Where does the light go when light strikes a mirror? It comes back, right? Things reflect. Because if the angle of incidence is 0, what's the angle of reflection? 0. So the light just comes right back. And our brains say, hey, that light took a long time to strike a mirror and come back. I'm going to create an image. And I'm going to with that light. We'll talk about that later. A concave mirror, like that mirror, this is the kind of mirror you might find if you have a shading mirror or a makeup mirror. It blows you up. There's a concave mirror. If you want to see how big your pores are, nothing's better than a concave mirror. Ah! Oh! Ah! Look out, it's coming at you. Here it comes. Ah! Look how huge you are. Oh, you're gigantic. Look how big people are. I'm enormous. Woo! Okay. So concave mirrors are great if you want to blow yourself up, which is why they sell them as makeup mirrors and shaving mirrors. Play with the mirrors later. So if you have three parallel lines and they strike a concave mirror, get this out of lanes, whatever. If you have three parallel lines and they strike a concave mirror, what do those lines do?
They converge together.
Yeah, they converge together. Because if you can imagine drawing tiny normals to each of these points, like this normal is easy, that's like right there, but this normal's right there, and this normal's right there. So there's a normal, so there's a normal, and there's a normal. If, let me put it on the other side of the arrow, then this one's going to go this way, and this one's going to go that way, right? Okay. The law of reflection still applies, because it's still just air, and so I do it a little less defined this way. So this is a converging mirror, where the rays converge to a point. Yeah?
So basically mirrors are like shaping the light you see.
Is that how telescopes work?
Very much so, yes. Now I want to show you something with this concave mirror. I need a volunteer. You can take your seat though. Okay, Bowen. So what kind of image do you see in the mirror right now? Upside down? Okay. Watch what happens when it comes towards you. What kind of image is it now? So it's upright, right? It's upright?
Yeah.
Sure.
I don't know.
That's upside down.
It's upside down.
Okay. So is it upside down or right side? Okay. Let me know when it's not normal anymore. Now, do you see the image at all? Or is this a big blurry mess? Okay. So you got upright, this is the word we use, upright here. And we got inverted over here. That's the sciencey term for upside down is inverted. So we got upright here, and we got inverted over here, and right between upright and inverted, you get nothing. The image is basically the light destructively interferes. When they come together, that light will destructively interfere, and you won't get any image at all. So here, what kind of image do you have? So inverted, and then now it's.
I don't like that.
Make it go away. So yeah, so you'll get an upright image here, and really far away you'll get an upside down image or an inverted image, and right in between the light rays will slam together, and they will. I'll let you guys play with these. They'll be around the room.
Do they cancel each other out?
Yeah. Well, yes and no. At the quantum level, they're doing a little bit of interference, both types. It basically just makes a giant mess. So yeah, they're canceling each other out. So we have a name for this point right there. It's called the focal point. The focal point is where the light comes together. Now, much less dramatic is the convex mirror. Very handy if you're walking around Walmart with lots of boxes and you want to run somebody over, or if you're concerned about kids stealing in 7-Eleven. You guys have all seen these, right?
Yeah.
They put them on the corners so you can see around corners, and they put them back in the back so you can see the kids, you know, taking cigarettes and stuff out of 7-Eleven. So, yeah. What kind of image is formed in this convex mirror?
Diaper.
Is it an upright or an inverted image? It's upright. Yeah. It's itty bitty. But it's upright, so not terribly dramatic, but it does allow you to capture a lot of information. A lot of the information gets squished down into this mirror. Question?
So that kind of looks like what you see in like a GoPro video. Do GoPros use convex lenses?
They use
It's like a fisheye.
right, exactly.
Yeah.
Yeah. They use an image. They use a lens that doesn't focus true. It's like a fisheye. So it's a big bulbous lens, so it can capture a whole bunch of information. Yeah.
What color is
Well, okay, so there's basically two parts to a mirror. There's a reflective material, and then there's something that makes the reflective material stick together. Ideally, a really good mirror will have just the reflective material and nothing else on top of it. These have a layer of plastic, which they try to make as thin as possible. But the color of the mirror is whatever the molecule, whatever the atoms that are reflecting light can reflect. So if you make that mirror out of something really, really good that can reflect all frequencies of light, like silver, the mirror is colorless. However, old mirrors made out of bronze or copper, they weren't colorless because bronze and copper can't reflect blue light very well. That's why they look kind of gold. So a silver mirror is silver, colorless. So it's all about the atoms and the molecules taking in energy, those electrons jumping up a level, and they come back down, they release that energy. Remember chemistry? Remember October from chemistry? So when energy goes into an atom, the electrons jump up their levels, then in an infinitesimally small amount of time, they jump back down and give off that energy back. So that's what's happening. So if the atom can basically absorb all frequencies of light and re-emit all frequencies of light, then the mirror would be perfect. That's usually the case for things like silver. That's why silver is so great. It's got tons of places to put the electrons, tons of levels to jump to. Older mirrors, they didn't. Silver was very, very hard to forge, so they didn't use a lot of mirrors. If you were in ancient Greece, your mirror, if you had one, if you were rich enough to have a mirror, your mirror was most likely polished brass. Good enough to see if your hair was in the right place, if there was parts of food in your teeth. Not so good for anything else. Okay, so convex mirror. Here comes the rays. Where do the rays go?
Oh, wait.
Out. Yeah. So you can imagine little planes. There's a plane there and a plane there with a normal there and a normal there. And the rays go out. So a convex mirror is a diverging mirror. The imaginary line that we place at the middle of the mirror, tracing back to the object, is called the principal axis. And once again, where the rays come together, we call it the focal point. Yeah, so hopefully you can see where the focal point is for a concave mirror. Does a convex mirror have a focal point?
No.
It does. It has, because obviously the light is coming together to do something. So it's in there somewhere. The convex mirror's focal point is behind the mirror. And it's what we call a virtual focal point. So if you were to trace these lines back, That would be the focal point.
This is a drill. This is an emergency announcement. Soft lockdown, soft lockdown, soft lockdown. Teachers, please follow your procedures. This is a soft lockdown drill.
No,
Landon's gonna just get stuck out there.
Oh.
What if you're like stuck when you get everyone around you? It's like, why does these just like pick someone else?
Or you go to the office. Just like
All these out there.
hard lockdown.
Hard lockdown?